Alright, so this will be the first proper session of regression. And let me ask you, what's the purpose of regression? Why do we do it? Why is it so hyped? And it is quite hyped, if you don't know. No idea. Why is- Okay, so I'm not going to tell you. I'm going to ask you again this question at the end of the lecture. Now, let me do an example. Let's say we observe ice cream sales and daily minimum temperatures. Okay, and let's say we do it not for several days in a sequence, but one day in a week, so that we have some variation in daily temperatures. So let's say any particular day, be it Monday, so we take Mondays again and again over several weeks. So we would have week 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. 23, these are degrees Celsius. 21, 25, 18, 13, 16, 13, 17 and 12. So you can tell we are in the later half of the calendar year in India, where minimum temperatures are falling. And let's say we observe for a ice cream cart these sales. Okay, now it's natural to expect ice cream sales to increase if minimum temperature increases. Okay, if people have to eat desserts, they might as well. One can expect them to prefer ice cream with higher temperatures and other things when the temperature gets low. Okay, let's plot this. Rupees. Is it coming out fine? Okay, now let's have some grid lines that I'm going to rub off later on. Now with 23 we have 3210. So 23 will be somewhere over here and 3210. Just somewhere. With 21 have 2090. 25 is 2250. Okay, let's get rid of the grid lines. Okay, so we have this. Now if I ask you, how do we approximate this relationship by a function? Okay. Now one may say that let's draw a line of best fit. Let's take our hand and take it right through it. Line of best fit. Okay, we have this word best, which till this point is undefined. What do we mean by best? How do we make sure that this is the best one? Okay, now we see that obviously they're scattered across, so we can't have a straight one which goes through every point. So we would have some deviations from our relationship. Okay, some of them are positive. Okay, this is positive. I'm going to use green for positive and blue for negative. Okay, now before drawing these arrows, it looked fine, just fine. Now after drawing these arrows, I have some doubt. This is not best because we have more of blues, slightly longer in length, less of green. Okay, so I would not claim this is the best that we can have. So what's the way out? One can say that if positives and negatives cancel out each other perfectly, then we may have a best. Okay, so not something like this one, but probably one which is slightly lower and slightly flatter. This is not the best. Let's see how the deviations come for this one. Okay, slightly better. Now we have more of the blue ones, but some of them are smaller. Okay, I would still not claim that this is the best we can do. This may not cancel out each other perfectly. If the length of all the green ones put together and the length of all the blue ones put together, they're exactly equal, then we may claim that this is the best we have. Okay, but then again there's a problem. We can have multiple of those lines in which the green ones and blue ones cancel out each other. Can move this slightly, length will be altered, they still can cancel each out. We can have a number of those lines again. So that's not again something best. If you have multiple, there should be one which should be above all of them. Now one way out of this problem is to say, okay, let's cut down this business of cancelling out. Let's take all these lengths, not as some positives, some negatives. Let's take all of them as positive, and then it's going to be a positive number, and then let's try to minimize that. Okay, that is possible, nothing wrong in that. The only problem that we would have with this, with taking modulus of deviations, is that mathematical treatment would be very messy. Mathematical treatments with mod functions is quite messy. Okay, so we are in the right direction, but we've encountered a mathematical issue. If you want to conduct tests which would involve mathematics, then we would face a problem. So we need another way of making all the deviations positive and still having it in a form that is easier to work with mathematically. Okay, squares of deviations would work. That's going to make all the deviations positive. We can sum that, and squares are very easy to work with mathematically. All right. There's nothing special with square, just square. Any number, positive or negative, raised to a power which is positive is going to make it positive. So, but there's no need to have more trouble than we really need to. So, squares would do just fine. All right. Now, I do have a line. Okay. If we fit a line which is equal to minus 353 plus on the hat. Okay, this is exactly the line that we have obtained by minimizing the sum of squares of deviation. Our objective in this series of lectures is, in today's one, how do we get this first of all, and two, what can we do further in terms of inference on this. Okay, now what we would have then is a line the slope of which would be 125, which to say that on average, as minimum temperature increases by 1 degree Celsius, ice cream sales for the kind of carts that we are looking at increases by 125 rupees. Okay, but that's again on average. Now let me now claim that this is the line that I have. Y, and there's a caret on top of that has called caret. Now what this is saying is that based on the sample that we have, this is just a sample. Obviously there are going to be more than one cards, more than these temperatures available. This is a sample that we have. Based on the sample that we have, we have drawn this relationship. Okay, now we can use this for predictions as well. What happens if the minimum temperature is say 27? Okay, we just go back to this and we can say that we should expect the ice cream sales to be that. Okay, if it's lower, or we just have few sample points. What happens if it's between 12 to 13, 13.5? You can just look at that. Okay, now what we see, which is of course that one would expect, as temperature rises, ice cream sale rises, but then on a day when the minimum temperature was 25, this was lower than what we expected. And 23, this was higher than what we expected. So what do we have here? Okay, what we have here is that minimum daily temperature is not the only thing that affects ice cream seal. There's a whole lot going. It's quite possible that on 23rd, on the day when although temperature was 23rd, India might have come out on a cricket match with our rival, so more people come out on the streets to celebrate and they see ice cream cart and they certainly buy ice cream and eat. Okay. On 25th, something else which should hold people back to their rooms. They would not. Okay. There can be a whole lot of things which can go on. And even if we account for all those things, what we cannot do in social science is predict human behavior perfectly. We're humans after all. So one fine day stars make a particular combination and people suddenly feel like eating ice cream. There's nothing we can do to explain that. All that is at work which is keeping, which is contributing to these deviations. Now what we can do with our function is that we can use it to make a claim that, let me draw another line. If it's a sample, we can get average for this sample as well, average sales. Let me say that this is somewhere around here. I'll call it y bar. Okay, so for this course, whatever we learned in statistics is going to hold. Y bar would be sample average, and we would say mu of whatever notation we use. If we're using y for ice cream, this would be for the population, and we would never know what this is because both patience and resources are in short supply. No one has the time to speak to all the cart runners what their ice cream sales is. So we're going to just use sample. The bigger sample, the better for us. Now, we can say that although this is the average, minimum daily temperature affects this. So for some, it's going to be above average. For some temperatures, it's going to be below average. And part of that deviation can be explained by our model and part will not be explained. Okay, so what we have is for 23, this is explained. Deviation. Our model says that we expected ice cream sales to be above average for this temperature, but we don't have any idea what's going on for this. This is unexplained deviation. Okay, we're going to have symbols for all of that. If you just open the text is filled with symbols and algebra. I'm going to go to that. Before that, what I want to do is make you comfortable before you get intimidated by all those symbols and algebra. Okay, does it make sense? Similarly, for temperature, this is, say, this is I think 18, 17, this one was 17. So we expected the average sales to be lower than average, but it came out to be further down. For whatever slightly lower, 16 or so, we expected this to be a lot lower. It was not all that lower. So this is the unexplained one. Okay, so from the point to the line is unexplained. It can be positive or negative. From the blue line, which is average, to the black one is explained deviation. Okay, now this is a simple model. There's nothing in the theory that says that we only have to restrict ourselves to one variable explaining it. We will deal with multiple variable regression where we can have, not going to do it immediately, but we can have one independent variable here, another one here, and the dependent variable here. You can also do that, but just like calculus, we're going to start with one variable, learn the tricks of the trade in one variable, and then we're going to move to multiple variable. All right. Now I already have one notation. This is predicted for our model. Now this is a deterministic relationship. Okay, what this says is we exactly know, based, if you just put different values of minimum temperature, we're going to get an exact value for our prediction. Okay, this stuff doesn't work in social science. It works in physics. It may work in biology. It doesn't work in social science. What works in social science is stochastic relationships. Okay, this is a stochastic relationship. What it says is we have a deterministic component, and then we always have one thing or the other affecting our relationship. So now I'm going to connect this yi are these actual numbers that we have. This is the prediction that we have. I can have another column with all the predictions. There would always be some difference, and that difference is the error, E sub I. Okay, we have a index here, I. That means 1, 2, 3, 4 is going to be different. Now, so we have this as, if we start with the first one, a very small error for the first one. This tiny thing. This is E sub 1. Then we have E sub 2. We have E sub 3. And we have no error for the last one. It's perfect. This is E sub n minus 1. E sub n is equal to 0. Okay. I'm doing this in such detail on purpose so that later on you don't have a problem with algebra. Okay. This one here is this on the line. What is this? This is y hat 1, y hat sub 2, just, and then y hat sub 3 all the way. This one is, okay, we already have it written there. This particular value would be y hat sub n. Since y hat sub n is equal to y sub n, we have E sub n is equal to 0 for the last one. Okay. Now, what did I say? How did we get this one? By minimizing the sum of unexplained deviations. Not deviations, unexplained deviations. So what are we doing? We have minimized what? Sum of squares is unexplained deviation, and we have n, small n, sample points. Okay, this is what we've done. Alright, I'm going to take the table out. This is the first, in the first one I actually thought it better to have some data points. Now not going to spend time again and again to make it according to scale. I'm going to just plot that dot 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 from here on. Okay, so everything here corresponds to the sample. we would of course have a population as well. Now, I would say that this relationship is just trying to figure out based on data what the true actual relationship is. So let me make a claim on what the true relationship is. That would be yi is equal to beta naught plus beta 1 to x plus ui. Okay, now here this I would range from 1 to capital N. Okay, this is from what we learned from statistics. For the population, it's capital N, but we would not have this data. What we would do is we would try to estimate this using our sample. So that would be yi. Now ideally my personal preference is to use beta naught hat, and I think corresponding I'll try to use notations which correspond to the text. Suppose it's beta 1 and beta 2 there. Okay, so my preference would have been to use beta this. Why? Because this is what we did in statistics. Said we have a parameter which comes from population. We get a estimator of that and we just use the same notation and put a caret on top. Okay, but again going to go with the text. What we have in the text is not beta 1 caret. We have small b1 and small b2. Okay, although it's not a caret, you must keep in mind that beta, this b1 and b2 are estimators. Okay, you must again remember the difference between estimators and estimate. Till we have this equation, okay, everything here is a random variable, because if we take another sample, we would have different sets of y and x. If we do our algebra and get this equation, we would get different value of beta 1 and beta 2. Take another sample, we would have different value. For any particular sample, if we have calculated values like those, beta 1 is equal to minus 3, b1 to minus 353, and b2 is equal to 125. These are estimates. Because they came out for a particular sample. Okay. Now, again, with this understanding, what we can do is we can do tests on this. We can approximate them with distributions, and unbiasedness, consistency, all those things would be applicable. So estimator. Now we're going to take special care of coming up with these estimators so that they satisfy certain properties. Okay, now beta 1 would be estimator of this one, beta 2 would be estimator of this one. One can expect E sub I to be estimator of this one. The catch here is we would do nothing to take care that E sub I is a good estimator. It is residual. If it's good, fine, we'll be happy with it. But we're not going to intentionally do anything to take care that it's a good estimator. We're going to do it just for these two. Okay. Now you can compare, and then you can say that yi will be beta 1 plus beta 2 xi plus ei. And yi is also beta 1 plus beta 2 xi plus ui. This is the true relationship that we would never know. That is the one we estimated. Now, I've just written the same thing over here. So, I'm going to use this space. Okay, like I said, nothing is going to be scale from now on. So, let's say this is again, care has been taken to minimize the sum of square. This is sample. Although we would never know, let's try to play God. Okay, let's say we did know. This is the true relationship. Now, multiple attempts, we would get something, then slightly off, then again slightly off. But our aim should be to take care so that slightly off is minimized as far as possible. It's not possible to have exactly the same thing, but to minimize these. Okay, we would also have this would come from the sample. Black one comes from the sample. Red one, we've just imposed it. Okay. Although I cannot stress enough that we would never know what this red line is. Now what do we have? Say we have a particular x value. Okay. X sub I. What is this? This is y caret sub I. Based on our sample, this is what we've done. We predicted that, let's take it down. This is the best we can do to explain. This is, in terms of our notation, what is this? Yes, this is yi. What this would be is, we would say, this would be the expected value of y given xi. Okay, this is the notation that we have. What would be these differences? From the point to the line, what's our notation? From the point to the black line, our relationship that we have estimated, E sub I. Okay, from the red one to the black one, it's, yes, it's U sub I. Okay. Now, just so that even the viewers have a snapshot, this is the, okay, you can take a snapshot this way. This is the thing. All right. Now, any issues till now? I'm going to get everything off. Now this q I in the true model for the population and this E sub I for the relationship that we have estimated. What's the role of this? Okay, one can capture influence of other variables which otherwise would affect, but we might have missed out or might have intentionally not included if we don't have data on that. Okay, might capture data errors. Okay, if you do this something like this in the real life, what are we going to do? We're going to go speak to ice cream sellers and we're going to ask भैया कितना sale हुआ. Okay, now he's not going to calculate, he's just going to give us an estimate roughly. This is what you have, and if you do this for multiple, then we're going to have errors. Hopefully positive ones are going to cancel out the negative ones. Whatever remains would not be explained by our model would get pushed into deviation. Okay, there would always be data errors for the kind of work these social scientists do. Okay, then because we're social scientists, this would capture the uncertainties related with human behavior. No matter how hard you work, how many variables you get, human beings are human beings. At times they feel like doing things, at times they don't feel like doing things. Okay, on certain days more humans would like to buy, certain days not many would like to buy. Okay, so what's the principle of Occam's razor? It says that keep stuff simple. Don't make it so complicated that it becomes useless. If you can capture a relationship with a simple model, you do that with a simple model. Alright, now if we intentionally keep out some variables which we think are going to have a minor influence on ice cream sales, but if we continue to include them, it's going to make our model unreasonably complicated. So we just take those variables out, but those variables will have influence. That influence gets pushed to error. That's something we would do intentionally, because for social science we cannot get either identification of all the variables, and even if we are able to identify them, how do we get information, hard numbers on them? So that gets pushed to the error. So this does have, these two have a role in our analysis.